Okay, good morning. This is Professor David J. De Los Reyes. It's April 13. The time is 12:08. Okay, my topic tonight will be one of the most interesting problems under advanced mathematics because we could now prove the importance of the so-called Laplace transforms. So my topic for tonight will be a series RL AC circuit. It should be AC. It should be energized by an alternating current source. So we will be deriving the total current as a function of time by using Laplace transform. Since the solution is actually very long, for the topic tonight, I will just discuss the complementary solution. And our next topic, next time around, I will be discussing the half portion of the total solution. Okay, let's proceed. I will check my camera. Oh, it's fine. My lesson for this morning will be Advanced Math, lesson number 30. Series RLAC circuit, the solution should be by using Laplace transform. Meaning, we are to solve for current as a function of time, okay, by using Laplace transform. Because the last time around, we already have solved this problem, but the solution is actually by using the so-called classical solution, that is differential equation. So for this morning, we will be discussing the solution of this same problem, but the solution should be by using Laplace transform. Since the solution is long, I will just present the so-called complementary solution. And the next time around, on the next lesson, lesson number 31, I will be presenting the solution of the so-called particular solution. Okay, let's proceed. The circuit is a series circuit, resistance and inductance connected in series, energized by an alternating current source. The equation of the voltage is E sub m sine of the quantity omega t plus angle P. So as soon as we close the switch, there should be circulating current. And the problem is asking what will be current as a function of time, okay, by using Laplace transform. Okay, this is another solution. Okay, let's try to bring out the solution. We take the summation of voltages and they should be equal to zero, sigma notation, meaning the summation of voltages should be equal to 0. That is after closing the switch. So plus E minus B sub R minus B sub L, and this should be equal to 0. Okay, let's try to put the value of E. The alternating current voltage is actually sinusoidal. Okay, and the equation is actually E sub m sine of the quantity omega t plus angle P. So I replace this small letter e here by E sub m sine of the quantity omega t plus angle P. And this should be equal to, I will place this 2 here on the right, so it will become IR plus L di dt. As always, the voltage across the resistance is the product of the current passing times its resistance. And the voltage across the inductance is actually its inductor times the rate of change of current with respect to time on that inductor. Okay? So actually, we are now given a differential equation. Okay? And the problem is asking what will be current as a function of time by using Laplace transform. Okay, I will try to expose. It gets dirty already. Hold on, I will get my wiping cloth. Sorry for that one, I get my wiping cloth, so my eraser is already dirty, so I must have to wash it maybe tomorrow. Yeah. Okay, let's try to continue. So we are now given this differential equation after taking the summation of the voltages. So by presenting the solution Laplace transform, I place it here, take the Laplace transform of both the left and right. For the left hand side, A sub m is constant, so A sub m, and the Laplace transform of sine of the quantity omega t plus angle p, we have derived that one already. It is one of the Laplace transform formulas. That is the equivalent of the sine of the quantity omega t plus angle p. It is actually sine or s sine of angle p plus omega cosine of angle p all over s squared plus omega squared. That's the equivalent of this. Okay? And for the product IR, R is constant, so it will be R. And the Laplace transform of both small letter I should be I as a function of S. Plus L, the Laplace transform of any differential thing, we have derived that already. So it will be S, I as a function of S, minus 0. This minus 0 here is actually the initial condition, and this should be 0. So for L, the identity, the Laplace will be L times the open bracket S, I as a function of S minus 0. And this is 0. So simplifying this one, I is a function of S. The common factor will be I as a function of S multiplied by the open quantity R plus LS. We just combine this one here. Right? The common factor is I as a function of S, the one we are looking for as a function of S, equal to, for the right hand side, I just interchange. I put this one on the left and this one on the right, and this should be equal to E sub m times the quantity S sine of angle P plus omega cosine of angle P all over S squared plus omega squared. And solving for I as a function of S, we will divide both sides of the equation by this. So I will just rewrite the left hand side, okay, 1 over R plus LS. Then I introduce the L over here. Meaning, this portion of the equation, I will try to multiply it by L over L. L over L is 1. Okay? So I as a function of S now will be equal to, if we try to insert this L here inside, LS over L will be simply S, right? And R over L will be R over L. I place it here. And the product of S squared plus omega squared, it is factorable to actually S plus J omega times the quantity S minus J omega. So, because if we try to multiply this one, what comes out is actually S squared plus omega squared. Okay? I combine them at the denominator. Can be written as a linear factor, two linear factors. This is linear factor. Okay? There's one L that remains over here. So I will put this L here over here. I will remove this one now. So what comes out for I capital letter S as a function of S is E sub m over L times the quantity S sine of angle phi plus cosine of angle phi, okay, all over S squared plus omega squared is actually the product of S plus J omega. Real part and imaginary part. We are involving, we are discussing what you call this, oscillatory conditions here. So S plus J omega, S minus J omega times the simplification of this after inserting L inside, which is actually S plus RL, closed quantity. Okay? So to bring out the solution, since there are three linear factors, we must have to bring out an unknown constants ABC to solve for the solution. So I will just forget E sub m over L for the meantime. I will just concentrate on S sine of P plus omega cosine of angle P. And this should be equal to an unknown constant A over S plus RL plus B over S plus J omega plus C over S minus J omega. And if you try to notice it, this portion here represents the complementary solution. And the sum of these two here represents the so-called IP, the particular solution. So for this morning, since the solution is a little bit long, okay, I will just present the solution of the complementary solution. That is, we will assume the value of S to be equal to negative R over L. You replace this S here by negative R over L, so it will become negative R over L sine of angle P, I'm following this, plus omega cosine of angle P, equal to, this A here, okay, the common denominator is actually the product of these three here. So if we try to multiply A over this, multiply by this quantity here, what comes out for the value of A will, the multiplier of A will be A times the quantity R square over L square plus omega square. It is the product of these two here. Okay? But we inserted the value S to be R over L, so it will become R square over L square plus omega square plus, what comes in? Plus 0 plus 0. This B here, okay, should be multiplied by S plus RL, but if S is negative R over L, this will be 0. So B times 0, okay, will be 0. Okay, and the value C, it will be C. It will also be multiplied by S plus RL, and since the sum of S plus RL is 0, C times 0 will be 0. So the coefficient, unknown coefficient C will be multiplied by 0, so it will become 0. So the last two part is actually 0. Is gone. So meaning, when we assume the value of S to be negative R over L, okay, the only unknown remaining is actually A. And if we try to simplify this one, it's an algebraic manipulation, a little bit long. But these are the explanations. And if we now try to compute for the value of A, it will be L times the quantity omega L cosine of angle P minus R sine of angle P over R square omega L quantity square. Omega is given, R is given, L is given. So the only unknowns are actually cosine of angle P. And from this, actually, don't be afraid with this one, because we are given the right triangle. For an impedance, the imaginary part is the inductance. It is, this is actually X of L. And the real part is the resistance. Okay? Adjacent side, opposite side, using your knowledge of the so-called trigonometry, Pythagorean theorem, if this is R and this is omega L, the hypotenuse is actually Z. So actually, we can formulate the relation of, or the connection of Z in terms of R square and omega L square. That is, if we try to square this one plus this, should be equal to Z square. So I place it here, R square plus omega L quantity square should be equal to Z square. And the angle between the impedance and the resistance is actually designated by theta. It's the first one is angle P, right? This is now theta. Cosine of theta is actually R over Z, adjacent over hypotenuse. And sine of angle theta will be opposite over hypotenuse. So I place it here, sine of theta will be omega L over Z. So going back to this equation here, it will now be L, the common factor. I will now try to compress what I call this omega L cosine of angle P. I will replace this sum here by Z square. It is this. I put it inside. Minus L open bracket R sine of angle P, again over Z square. Then I will try to algebraically manipulate. A now will be L times open bracket. I will take omega L divided by 1Z and the other cosine of angle P divided by 1Z, because Z times Z is actually Z square. Minus L, open bracket. I will put 1Z over the R, so this will be R over Z times sine of angle P over Z, because Z times Z is actually Z square. And if we try to take the equivalent of this, omega L over Z is actually sine of theta. And if you go back to the impedance right triangle, R over Z is actually what is cosine of sine of theta. Now, cosine of theta, right? So, after replacing this omega L over Z and R over Z by their equivalents, what comes out now will be there is one Z that remains underneath, so I will bring it out, so it will be L over Z times sine of theta cosine of angle P minus cosine of theta sine of angle P. And if we try to move this one as a first thing, okay, I will put L over Z here, but if I want this to be ahead, okay, I will put a negative sign over here, because negative L over Z times this is actually the second one. I will make this thing as the first one, so it will be sine of theta, sine of angle P, cosine of theta. This will be next, right? But this is minus in the minus, so this is actually the first one, yeah, right? Cosine of angle P, sine of angle theta. And I place it here from the so-called difference of the sine of double angle, that is sine of the quantity angle P minus theta. The expansion is actually this. If you try to go back to your trigonometry, I will check my camera again. It's still fine. So what comes out now? Meaning, A now will be negative L over Z, and the compressed equivalent of this is actually sine of angle P minus theta. So, A now will be negative L over Z, sine of the quantity angle P minus angle theta. Okay? So, for tonight, I will just be solving this one here, and this represents a complementary solution. So, I, as a function of this now, I will be following this. A sub m over L times this first quantity, except for the 2. Because the 2, I will continue that the next time around. Okay? Sine of quantity angle P minus theta times the linear factor A over S, right? So this is 1 over S plus RL. Because this value here should go back there, but if we try to simplify, it will become negative E sub m over Z, sine of quantity angle P minus theta times 1 over S plus RL. Then taking the inverse Laplace transform. We are just solving for the meantime the complementary solution. So the inverse Laplace transform of the I capital letter A as function of S, considering this one, should be equal to, these are all constants, so we bring it out, okay? E sub m, negative E sub m over Z, sine of angle P minus theta, the inverse Laplace transform of 1 over S plus RL. And this is similar to 1 over S plus A. And the last time around, we solved this that this is E raised to negative 80. Right? So the inverse Laplace transform of capital letter I as a function of S, considering for the meantime the complementary solution. So what comes out for this will be the complementary solution, equal to negative E sub m over Z, sine of angle P minus theta. The Laplace transform equivalent of this, if you go back to your Laplace transform table, it will be E raised to negative R over L times sine. This is actually the complementary solution of I as a function of time. Because if we try to recall the total solution for RLAC, this was actually the solution from the classical solution, that is I particular plus complementary. The particular is actually E sub m over Z, sine of the quantity omega t plus angle P minus theta, minus E sub m over Z, sine of angle P minus theta, E raised to minus R over L times sine. And actually, this is our computed complementary solution. We are just on this part. So the next time around, we will bring out the solution of the particular solution by using Laplace transform. That's it, guys. So we just finished the complementary solution for tonight. So on the next lesson, we will discuss the particular solution, because it's a little bit long. It's long, right? the algebraic manipulations law. It involves the knowledge of impedance things because we are discussing alternating current circuits. So this is for you guys. So for those persons who are taking advanced mathematics, this is for you guys. Okay. If you want to subscribe to my channel is at youtube.com/@ProfDavidJ.Reyes. And if you want to share it, please click share. Good morning from Los Angeles.